Hey everybody, in this video we're going to look at some trade-offs between spatial, spectral, and temporal resolution in satellite imagery. So there's four types of resolution we might think about in remote sensing. Radiometric resolution is essentially the range of energy or radiance that is recorded by any given digital number, or that's mapped into any given digital number. And this really amounts to what levels of brightness can I resolve, right? If a large range of brightness has been mapped into a single digital number, you can never resolve anything below that increment of brightness. Then we have spatial resolution, essentially the pixel size of the image. Really amounts to what is the smallest object I can resolve in my image, right? Smaller pixels are going to let us resolve smaller things. And spectral resolution, this is the width of each spectral band, measured usually in nanometers. In other words, this is the range of wavelengths within which a given band was collected, right? So for, the red band, it might be, 600 to 700 nanometers or something like that. And obviously, if you have smaller bandwidths, a more narrow range of nanometers, you can more easily discern materials that have similar spectral signatures. And then finally, we have temporal resolution. How long does it take to collect repeat images of the same location on Earth? How often does the satellite pass overhead? And this essentially boils down to how frequently can I monitor some process. For example, for agricultural crop health, you might need every 2 weeks. For wildfires, you might need every 2 hours. For weather, you might need continuous temporal updates. So those are the four types of resolution. And let's start by digging into spatial resolution. So I'm going to show you 3 examples of the exact same image. Here's Landsat band 6. It's a 60 meter pixel size. So each of these square cells is 60 meters in width. If we step up to band 3, which is a 30 meter pixel size, notice how much detail we can start to resolve. We can resolve some linear things, probably roads. This curvy black thing here, what could that be? Well, if we go to 15 meter pixel size, suddenly it's clear that that actually is a river. That's Otter Creek. So the advantage of spatial resolution is quite clear. It really lets us pick out a lot more detail in the images. So what determines spatial resolution? To talk about this and to use this as a launch point towards understanding trade-offs, I want us to start by considering a simple camera geometry. This is called a framing geometry, a framing camera. So essentially the way this works is you have some detector chip back here. Actually, let's start on the ground. You have some ground element called the instantaneous field of view. That might be square, but it doesn't have to be. Light reflecting off this ground element goes up to a lens right here. It gets reflected through the lens, which then, refracts it back onto the detector chip here, right? So the idea here is that every point on the ground, photons go up and they get refracted to some specific point on that detector chip. And the detector chip is essentially recording how much energy comes from each point on the ground. So if we consider this as a whole, the geometry of a framing camera is governed by this pretty simple ratio relationship. And understanding this really actually gives us our first look at some of the trade-offs between spatial resolution and temporal resolution, for example. So what this says, right, is the ratio of the dimension of the field of view over the height of the satellite must stay equal to the dimension of the detector chip divided by the focal length of the camera. So it might be pretty desirable, for example, to have a larger instantaneous field of view, have G be bigger, right? But if you wanted G to be bigger, you would also have to increase H. You'd have to fly the satellite higher in order to maintain this simple ratio relationship. Or if you wanted G to be bigger, perhaps you would increase the size of the detector, right? So that a proportionally larger detector could map a proportionally larger field of view on the ground. But of course, there's all kinds of technological limitations to how big the detector can be, how long the focal length can be, and so on. And this is a wonderful field of sensor design, essentially, that I don't know much about, I will add. So let's look at this idea of the detector. Okay, let's explore that a little bit more. As I just said, it defines the size of the image plane. So it defines the image plane back here. And we're going to see in a second that it actually breaks this image plane into a bunch of discrete pixels. And it records light by converting photons into electricity. And the way that it does that is because most detectors are made of charged coupled devices. They are CCDs. Essentially, it is a semiconductor material. When a photon strikes it, the photoelectric effect turns that photon into electricity, right? So the more photons that hit your detector, the more electricity you generate, and the bigger your signal is. And that's how we make these measurements, right? We turn photons into electricity, and the more electric energy we produce, the brighter something is, right? So that's the relationship. Brighter equals more photons equals more electricity. So importantly, these detector chips, these CCDs, are broken into an array of what are called photosites, usually on a square or rectangular chip. And each photosite converts photons into electric current on its own, right? They're basically like individual detectors within this larger detector chip. And the electric current measured or recorded by any photosite is proportional to a couple of things. The number of photons, right? More photons is more energy. And also the energy per photon, right? We talked earlier about how blue photons have more energy than red photons. So it'd be easier to measure a signal made of blue photons than it is of red photons or of infrared photons. And of course, exposure time matters. If you keep your shutter open for longer, you're going to count more photons. So here's an example of a detector chip. This is pretty outdated, but it gives you the idea. Here's the chip itself, and the best model of this chip has 4096 by 4096 pixels or photosites. Each one is 9 by 9 microns, right? They're these tiny, imagine 9 microns is very small. And this is outdated. I'm sure a modern detector, the photosites are much smaller than 9 microns even. So, but that's the idea. And just to reiterate, because these detectors are broken into a bunch of smaller pixels or photosites, individual pixels or photosites obey the same geometric relationship as the detector, right? So if your goal is to reduce the ground pixel size of an image, right? You want a higher spatial resolution. How might you accomplish that? Well, one thing you can do is you can pack in more smaller photosites onto the chip, right? So now we're talking electrical engineering. We need an electrical engineer to design a better chip that has more or smaller photosites. Okay, but that may come at a cost. Each of those photosites may be able to collect less energy because they're smaller, right? You can fly closer to the ground is another one, right? So if you fly closer, you're going to take this geometric relationship and essentially you are going to shrink down G and get smaller pixels. But that's going to come at the cost of the total width of your field of view, right? So you'll have smaller pixels, yes, on the ground, but your total width that you're imaging will also be a lot less. which guess what? That's going to affect your temporal resolution. That means with a smaller instantaneous field of view, you can't cover the Earth as frequently, essentially. Okay, so I want to kind of formalize this idea. So why can't we, for example, just pack in more photosites onto a chip and make them kind of infinitely small and just grid out an area into smaller and smaller photosites? The answer is that we need to maintain some signal to noise ratio, okay? We're trying to make a measurement here, and we need the signal we're measuring to be much larger than the noise, right? We need that ratio to be high. So where does our signal come from? The signal, as I've just said, is the total energy received at the sensor lens, right? That's the signal, brought there by the photons. Then we're going to actually spread that total energy across some number of photosites. And so here, we're just dividing that energy that hits the lens into some number of photosites. If you're dividing across more photosites, guess what? Each photosite gets less energy, gets a lower signal. Then we're going to actually further divide that signal because we're going to collect copies of the same image in different spectral bands, right? So let's say your image has 10 different spectral bands. Well, of the total energy that arrives at a photosite, you're now only going to measure some fraction of it that might be in the blue wavelength, or some fraction of it that's in the infrared wavelength, okay? So we're going to reduce it by another factor. And then there's dwell time. How long is your camera shutter open, right? You're typically receiving some power, which is energy per time, and you multiply that by the dwell time. The longer the shutter is open, the more total energy you receive. So these are all the factors that determine your signal, right? And you see each of these corresponds to one of our kind of resolutions, right? More photosites is higher spatial resolution, but less signal. More narrow spectral bands is better spectral resolution, but it's less energy, right? And dwell time is usually determined by orbital constraints that we'll talk about in another video. And then all of these signals are ratioed over noise. And I don't know much about this, but electrical engineers, we can't design perfectly tiny little detector chips. There's always going to be electrical crosstalk in a system. There's always going to be some background electricity flowing around the detector, stray measurements. So you always need to have enough electricity reaching your photosite that it is quite a bit above whatever the dark noise of your detector is. Okay, so how can we increase signal to noise ratio? I think you're getting the idea, right? We can have larger photosites, which accept more photons. We could have larger ground pixels that send more light to a given photosite. But both of these require lower spatial resolution. Likewise, we could measure across a larger spectral bandwidth, okay, and get more energy that way, but that's going to require a lower spectral resolution. So we're setting up a lot of trade-offs here. So just to show you an example of how this plays out, here are the bands for Landsat 7 and Landsat 8, okay? And notice a couple of things about this, right? In general, the bandwidth gets wider as you go towards higher wavelengths. That's because the photons out of these higher wavelengths, these far infrared photons, or thermal infrared photons, have very little energy. So you need a lot more of them to build up a measurable signal, right? So that's why, for example, on Landsat 7, band 6, it spanned a really big range of wavelength because it needed more photons to get more energy. Over here, the blue band is pretty narrow because a given blue photon has quite a bit of energy. And then we can look at this another way and also see that here's the panchromatic band, okay, for Landsat 7, band 8, and here it is, the panchromatic band for Landsat 8. So these are both 15-meter pixels, right? They're much better than the typical 30-meter pixels of these other visible bands. The reason that these panchromatic bands can be 15-meter pixels is because they are integrating photons across a wider bandwidth, or a panchromatic, a pan color. They're integrating photons of multiple colors, right? Panchromatic. And that gives them enough energy that they can divide their detector chip into more photosites and get out a 15-meter pixel size. So that's just a great example of how these trade-offs play off against each other in design of the Landsat system. And just to tie this all the way back to a previous video, why is this, right? Why does this all make sense? Well, it all comes back to the black body spectra and Planck's equation. We know that hotter objects like the sun, they are peaked in the visible. So most of the photons that we get from the sun come from the visible. There's just a lot more light in the visible part of the spectrum, and those photons have more energy. Once you're out into the far infrared or the thermal infrared out here, there's just not many photons coming, far, far fewer, and they have lower energy. So the take-home point is it is much more difficult to image things at long wavelengths because there's fewer photons and they have less energy. And that means bigger pixel size. So to kind of try to summarize these various trade-offs, right? If you want to have high spatial resolution or small pixels, you may need to have a wide bandwidth or a smaller instantaneous field of view, which means worse temporal resolution, okay? If you want to have high spectral resolution, i.e. narrow bands, you may need to have larger pixels to generate enough energy, or you may need to have a smaller field of view, i.e. worse temporal resolution. Now, if you really need high temporal resolution, so you are designing a weather satellite, for example, that wants to have data all the time, or something to monitor the ocean circulation that needs daily data or better, then you're going to need large pixels and a large field of view, which are going to give you worse spatial resolution. So all of this stuff makes my head spin, I have to say, but let's just end this video with a couple examples that might help solidify things. So here's a picture of pixel size in a lot of common satellite sensors, and then I've put here the ones that have local coverage versus global coverage. So these smallest pixel sizes, QuickBird, Iconos, Spot, these tend to only have local coverage, right? They get tasked to take a picture of a very specific place on Earth at some point. Usually these cameras can point in some direction or another. They don't just look straight down. In contrast, as we come to higher pixel sizes, for example, the Landsats here, this is where we start to be able to have global coverage. Landsat has a global repeat time of roughly 2 weeks, so it goes back to every spot on Earth every 2 weeks. And some of these sensors like Terra Modis, they do a lot better than that, even daily or every other day. But they pay the price in pixel size. And here's another way to look at that trade-off. We've got spatial resolution coming out here, and kind of temporal resolution or updating frequency here. So the best spatial resolutions, like Spot, tends to have a repeat frequency of many months to a year. And as you come down to the largest spatial resolutions, here's 1 kilometer pixels. These may begin to have even daily repeat times. So there you see that trade-off between spatial and temporal resolution. And here's another cool plot. I won't go into this in detail, but basically plots the number of spectral bands versus the ground resolution. And you can see that indeed, in general, satellites with more spectral bands tend to have higher larger pixel size. And then finally, I'll just finish this all off with a figure that shows essentially, this figure makes the point that different applications require different combinations of spatial, temporal, and spectral resolution. Okay, so for example, if you are working on weather prediction, you're fine with 5-kilometer pixel size, but you need a temporal resolution on the daily or hourly scale, right? If we're doing emergency response, for example, right, like wildfires or earthquakes or something, you need very good spatial resolution and you need really good temporal resolution. So that's a difficult spot to fill. Forestry, geology, we need kind of intermediate spatial resolution usually, and we don't usually need really high temporal resolution. If you're studying rocks, it's okay if the satellite only gets back every 10 years or so. But that's not true of all applications. Coastal processes, earthquakes, volcanoes, those do require definitely better temporal resolution. Okay, thanks so much, everybody. In summary, we have 4 types of resolution: radiometric, spatial, spectral, and temporal. Spatial resolution is determined by the number of photosites and the instantaneous field of view on the ground. The ground pixel size is generally limited by the signal-to-noise ratio, and maintaining a high signal-to-noise ratio requires trade-offs between spatial, spectral, and temporal resolution. And typically satellite sensors are designed for specific applications, with Landsat and Sentinel, for example, being kind of workhorse that try to strike a balance between some spectral resolution, pretty good spatial resolution, and pretty good temporal resolution. Thanks, everybody.